So now that we understand what a count file is, let's load some data into RedBase. The very first thing that you need to understand is that the allele frequencies that we observe at the count file do not really represent POMO states, and the reason is because there's a sampling process in between. For example, imagine this situation. I have a population of 100 individuals. One of them has the A allele and 99 of them have the C allele. If I sample 5 individuals from this population, it is very likely that I obtain 5 individuals with the C allele. So when I look at the counts, I may think that this state was fixed in the original population, but this is not true. It was actually polymorphic. However, the A allele was at a very low frequency and was not sampled. So these sampling biases have to be corrected, and for that we use this weighted sample method. What it does is that sometimes an observed fixed state is coded to a polymorphic one. But before continuing, let's see how or what are the files that you need to perform this tutorial. So here you have the data files that you need. Of course, you have the counts file for the gray apes, and it includes 1000 sites, and these are just the recoding of the count file for the case of POMO3 and for the case of POMO2, and we use natural numbers to do that, and that's why the name is here. And this is sort of a format that RedBase can easily read. Regarding the scripts, we have of course the weight sample method, which is implemented in C++, and these are scripts that we use to do the recoding. And of course we also have the RedBase scripts to run the POMO3 and POMO2, or meaning to do phylogenetic inferences with POMO3 and 2. And this is essentially what we need. So let's see how it works. So the first thing that we have to do is to recode the count file into the POMO3 and 2 state spaces. To do that, we use this R script. So the first thing is to either install our CPP or just load it, and I just did that. And then we just load as well the weight sample method into R, so it's here. And then we need some information, or we need to give some information. The first one, what is the name of the count file? This is it. How many alleles are there? 4, A, C, G, T. And what is the size of the virtual population? Because we'll be first doing inferences with POMO3, the virtual population size is 3. So I do it, and then I just click, this is the function, and it will be starting to do the translation. So as you can see, this was really fast, but this is happening. So essentially, what it's doing is recoding the count files into this state space here, okay? And one thing that we know, or I will tell you now, is that the fixed states are the first one to be coded. So the 3A is 0, 3C is 1, 3G is 2, and 3T is the state number 3. So let's see what's happening here. For example, in this case, the allele count is informing that 20 of the individual sequences had the T allele, is in the 4th position, and indeed it recoded it as a fixed state in the real population as a fixed state T, which makes sense. But let's now look at a count, for example this one here, which has 2 individuals sequenced has an A, but when we do the recoding, if this would be a fixed A in the POMO state space, this would be represented by the number 1, and we see 6. This is actually a polymorphic state. So of course only 2 individuals can tell very little about the allelic composition of the population. So benefit of the doubt and the weight sample method converts this observed fixed state into a polymorphic state, and this is essentially what this method does. So let's see what's the final aspect of this natural numbers type files. So this is just my working directory, so I call it POMOS. I included a data folder, an output folder. I have the Rebase executable here. This is just, again, the C++ weight sample method, and also the R script that we just used, and the rev scripts, and of course the counts file for the gray apes. So what we need to know now is to see what natural numbers type file for POMO3 is, and as you can see, is quite simple. So it has the name of the population, species, wherever, and then the states are here. So most of them are monomorphic or fixed, as you can see. Most of them are zeros, ones, twos, and threes, but we can also observe some polymorphic states here. So yeah, the recoding was done, and now this file can be read by Rebase. So let's move to our place, and yeah, in order to read these natural number type files, we use this read character data delimited function. So first we tell where our file is, and we know it is inside data. We have to tell how many states does it have. It is 16. So of course you don't have to know that. If you open your R script, whenever you do the state translation, one of the informations that you will get at the end is the number of POMO states, which is 16 for a virtual population size of 3. So you just put this number there. For POMO2, this is not 16, this is 10. So we put 16, the number of states, and then the type, of course, we have to define the delimiter, which is just the space, and if there are some headers, which they are not, so we just put false. So let's read this. So I'm here at the POMOS folder, and I just read the Rebase. Sorry. Okay, I'm inside, and now I just paste. So now I just print the data to see if everything is okay, and it seems to be. So first, the number of taxa is 12, which makes sense. This is the number of gray ape populations we have in our alignment. The number of characters or the number of sites is 1000, and the data type is natural numbers. So this all makes sense. So we are able to load a POMO3 type character inside Rebase, and of course we are now able to do inferences. But before starting to define the model, let's to define some variables that will be important for later. The first variables that we want to specify is the number of taxa, which we know it's 12, the number of branches that will be useful for estimating the phylogeny, and the taxa names. So we just copy, paste again, and as you can see, n taxa should be 12, and it is, and the taxa names should appear now. And yeah, so everything seems to be working right. Another thing that we need to define is to set up a variable that will hold all the moves and monitors of our analysis. So if you do not understand what this represents, you should probably redo the tutorial regarding the standard nucleotide substitution models. But essentially what these two are doing is just to store all the moves and monitors for our model.